Today, I will show you how we added KotlinX Serialization to SavedState. I will also explain how this change helps us build navigation tree serialization, and I will share how you can create your own codecs and maybe some problems that we found along the way. Before I start, a quick disclaimer is that this is a bit of a niche talk. It's targeted for library authors that needs or wants to build their own codecs for specific reasons. But if you're curious about how that was done in SavedState navigation tree serialization, that also might be interesting for you. So today we're going to talk first about why we need serialization support in SavedState, how our codec, encoder, and decode works. We will check the SavedState serialization code together, so you learn how to build that yourself in case you need it, and how navigation tree serialization use all of that. Last, we will talk about the problems we face and what we learned from that. So let's get started. We will begin with why we need KotlinX Serialization support. Android sometimes queue your apps when it needs memory. Users will expect the app to look the same when they come back. And how that works is basically, let's say your app goes to the background, Android calls onSaved instance state. That allows your app to save the state. And later, when the user comes back to the app, Android calls onRestore instance state to restore your data. This allows your app to restore to exactly the same place as before and make your user happy. SavedState is our solution for saving and restoring state. It works across platforms. On Android, it uses a bundle. On other platforms, it uses a map in KMP. And note that in Kotlin multi-platform, you can't use parcellables. So how the implementation looks like is basically this. We have a common class called SavedState. On Android, we have a type alias for android.os.bundle. On non-Android, it's implemented as a simple class that delegates to a mutable map of string any. In common main, we also have some functions that allow you to mutate the SavedState. Read allows you to read data from it, and write allows you to write data. Both our functions are in line, so there is no extra overhead to runtime for calling that. On Android, that is basically like calling bundle.putInt, getInt, etc. That's how the SavedState reader looks like. It's an expect value class, so there is no runtime penalty to use that. It's expose types, typed getters like getBoolean, getChar sequence, and all of the common bundle ones. And this is the writer. It's also declared the same way, the same thing, but for writing values. So our idea here was simple. We want to build a multi-platform serialization that you can take SavedState in any platform. So you can encode an object into a form we can store, and later we can decode it back. SavedState doesn't really care about how that happens. So KotlinX Serialization was a natural fit for us. It works on all platforms. People from the community like it. It's very popular. And you can just serialize, put this annotation serializable in your data classes, and it's work if you're using the compiler plugin. And it's very easy to extend as well and build your own thing. So let's build a codec together. But first, let's set the scope of what we're building. We will build our own encoder and decoder for SavedState. They must work on all platforms, and it must be optimized for Android, for bundle on Android. So there is no performance issue by using that. And any class marked with serializable should work with this codec and also work with other codecs. So you can take your serializable class and use whatever codec you prefer, or our one. That's our requirements here. So let's start with the serializable data type. Here is a plain user. It has a name, a string, and an age, an integer, and we mark that with the serializable notation from KotlinX Serialization. Now the encoder. The encoder tells the serializer to write the value. For objects, when you're encoding an object, it works step by step. First, it's going to call this method called beginStructure. Then it goes field by field, encode element for index 0, then 1, then 2, and so on. And finally, it closes with the end structure. For lists and maps, the idea is the same. we still start the structure and go element by element, but for list, the index is going to be from 0 up to n-1, where n is the size. For maps, it's similar, but we use even index for keys and odd index for values. So this is our SavedState encoder. We're going to show the actual code from our encoder now, and we're going to go through each method together. It follows all of the requirements from the encoder interface from KotlinX Serialization, but it writes the data into the SavedState. It implements the encoder interface, and it also implements the composite encoder. That way, it can handle both single values with the encoder interface and the structured objects with the composite encoder. Here are all the methods we need to write for our SavedState encoder. It does look like a lot, but actually most of these methods are very similar. They just handle different data types, like numbers, text, booleans, and so on. On the next slide, we're going to see how to make this simpler, but that's all of them. So instead of using the interface itself, we can use, instead of implementing both interfaces, we can just extend abstract encoder. This gives us most of the logic for free. You just need to override the parts that you care about in your codec. The rest goes to the full implementation. So by using the abstract encoder, we don't need to write every method from the encoder interface. It already gives us the default implementation for most of them. The only thing we actually need to always provide is going to be the serializers module that has the configurations for open polymorphism, contextual polymorphism, and so on. For SavedState, we accept a SavedState configuration. That is where we get the serializers module from. And how this looks is basically a class that has a bunch of properties. They are optional properties that allow you to customize how our serialization works with SavedState. The serializers module is where you're going to register all the custom serializers that you have, polymorphic types, and so on. The class discrimination mode controls how polymorphism is encoded. By default, it's going to use polymorphic. And encode defaults, if set to true, you're going to always encode all the properties, even the ones that have default values. By default, it's false, because we don't need that for SavedState, but you can set this to true if you want debug or testing or so on. It's worth noting this default serializers module. It's the module we provide out of the box with serializers that is used for most cases. So for example, it registers a SavedState serializer, was contextual. It also registers a multiple state flow serializer. It has some default Android specific serializers like size. And yeah, these types are types that show off in Android apps. And we include them by default, so just for convenience. So let's implement our first method, the begin structure. If you are at the root level, when the key is an empty string, we just return this encoder, and that way we are basically flattening the structure. So we don't wrap this type inside another SavedState. For example, in the case where you have a pair 3, 5, you would return just one SavedState with key first in 3, second with value 2, and we wouldn't be putting a SavedState inside a SavedState if we don't need that. So otherwise, it's not the root. It means we need to create a child SavedState. We call this SavedState function that is a factory function to create one. Then we link it back to the parent with put SavedState, key and child state. And finally, we return a new SavedState encoder that we will write into this child state. This lets us encode nested structures correctly. Each child object gets own SavedState, and the parent keeps track of where it belongs. Next is the encode element function. Here is basically how we're going to be tracking the key for each element. We keep a variable called key, which starts with an empty string, which is our root. And then inside the encode element, we set that key to the element's name using the descriptor. Then we're going to return true to let the serializer know that this element should be encoded. If returns false means this element should not be encoded. And we're skipping that. And these are the methods for writing values. We have one for each basic type, like Boolean, int, long, float, and so on. And we just write into the SavedState using the current key. For example, encode Boolean is going to call put Boolean with the key value, encode int, etc., and so on. And this is the encode serializer value method, which is used for encoding complex objects. So if you pass in the object, your codec will be called this method eventually, and it's going to handle these objects. First, we check for any platform-specific types. If the platform knows how to encode the value, we use that and stop. For example, in Android, one of them is parcelable. In encode format-specific types on platform, we check if the value is a platform-specific type. For example, as I said, the parcelable. We're going to call the built-in serializer that we provide parcelable serializer. If it's a Java serializable, the interface, we call the Java serializable serializer. If it's a type we don't recognize, we return false, so we let the normal path handle it. If not, we return it, which on fast path types. For example, an int list is stored with the put int list because the bundle has this method and is a bit more optimized and so on. And a string list is stored with put string list. If we don't recognize any of these types, we fall back to the default behavior from KotlinX Serialization. So why this matters is basically that it gives us the best of both worlds. If you're using the SavedState Codec, you get platform optimizations when they exist. If you are running in a different platform, we are using the default implementation and so on. So the decoder works in the opposite direction, but it's more or less the same. It's going to ask the serializer to read the value. For object lists or maps, the flow is going to look like this. You begin the structure, you loop through the code element index. For each index, we're going to be calling the writeDecode method, and finally finish with the end structure. And this is the full SavedState decoder. This is the SavedState decoder implementation. It's the same idea, but reversed. The begin structure, again, from the decoder. If we are the root, key is empty, we flatten the object as we did with the decoder, with the encoder. If it's not the root, we read the child save state from the parent, and we return a new SavedState decoder from that child. So we are basically traversing the nested structure that we created with the encoder. And this is the decode element index of the decoder. It's a bit longer and a bit more complicated than the encoding one. First, we need to decide how many elements we want to check while we are decoding. For lists and maps, we're going to use the SavedState size. For classes, objects, we use the scheme size because optional fields might be missing when we are saving this data. Then we're going to loop over all the index. Again, we're going to return the element name from the descriptor. If the element is optional and not in the save state, we skip it. The default value is going to be used. Otherwise, this element is present or required. We are going to set the key with the element name and return the current index. We also increment the index for next time this method is called. We start from the same place. If we finish the loop and there is nothing else to loop through the index, we are going to basically return the code done to let KotlinX Serialization know that there is nothing else for the coding. So these are the code methods. Again, it's very similar for the Boolean, int, long, float. For the basic types, it reads from the save state using the key that we just loaded. And this is the decode serializable method. We're going to do the same thing. We're going to call the decode methods using the platform-specific types. We're going to decode the value. We're going to just use that if it's available, and we are done. In the decode format, specific types on platform is also similar. We're going to use the serializes descriptor to figure out if we are able to handle that on Android. For example, if it's parcelable serializer, and so on. If it's not recognized type, we return null and allow the rest of the function to continue. If not, we check for the fast path types. And if it's not a type of recognize, again, we use the default serialization behavior and call the super method. So let's do a small round trip, a full cycle of serialization. First, we will encode the object that we saw before using the same serializing module. We will store the result inside SaveState. Then we will decode it back, and the result should be equal to the original object. So here's our user again. We're going to create a new instance, John Doe, 37 years old. We would call this method called encode to save state to encode the user. This is a public function that you can call in your code. How it looks like is takes three things: the serializer, the value, and the save state configuration. We make a save state encoder, which is an internal class. Then we're going to ask it to encode the value of the serializer, and then we return the save state result. How the encode flow is going to work is it starts with begin structure, the descriptor. For the first field, name string, KotlinX Serialization is going to call encode element with the indexes of 0. Then encode the string with the value in John Doe. For the second field, age int, it's called encode element with the next index. Then encode eating with the value. Finally, to finish with the end structure. And then now we're going to just decode it back, the same thing we just encoded. This is how the function looks like. The code from SavedState function, we're going to create a SavedState decoder. We're going to ask it to decode the value with the serializer. Then we return the decoded object. And the flow for decoding is going to call the begin structure first. Then the code element index with return 0. So we call the decode index method that is going to return us John Doe, the string. Next, the code element index that's going to return 1, and we use that to know what we want to call, and we're going to call the code int that takes 37. Then, because this class just has these two fields, properties, we're going to call the decode element index, returns the code done, and that means that there is nothing else for us to decode here. It ends with end structure, like the encoding flow. Last, we would check the original content in the code. Uses are equal, and they should match since both are data classes that implement equals. So should you build your own codec if you want? So the answer is probably not, unless you really need something, a custom format, like binary specific format, something domain specific, I don't know. And in the most case, someone already built that. So it's better to check the supported formats in the KotlinX Serialization GitHub page and docs. Contribute with that codec, or if not, build your own. That's basically what you need to build a codec. So let's talk a bit about navigation tree and how it works with serialization. This is where the SavedState codec that we just built is going to be used, and it's more, I guess, interesting to see in practice. In navigation tree, a backstack is just a list of t any. You own this list, so you're fully under control. You decide how to implement it the way you want, how to save it, whether it's with your own types, your own codecs, serialize, and so on. And here is how you would define the keys and arguments. In this case, we have a home object and a simple product class with just an ID string. Then we create the backstack with the initial key. This is compose code, let's say. So we would call mutable state list off to be observable. And that's the backstack. And that's kind of all. It starts with the initial key that is home. Next, we would use remember mutable state list of home to remember state between compositions. So we are sure that during composition, we're not going to be recreating the whole backstack. Users generally want to come back again to the app in the same state they left. So actually, the right API here would be remember serializable, which is a public API we provide that it's very similar to remember savable, but puts it inside uses KotlinX Serialization to do the saving. That way, the backstack is remembered in memory, but it also saved and restored with serialization. This is the remember serializable function. It's a generic composable that works with any type T and takes the input to trigger recomposition, a serializer for type T, a SavedState configuration for defaulting to our provided config, and init block to create the initial value. Is very similar to the other remember savable. And inside these, we build a saver using the serializable saver. This one is an internal function of ours, but it's very simple. And we call remember savable itself, passing the saver and the init block. And that's going to give us a remembered in compose and save it restored with KotlinX Serialization in case of a process death. This is the internal serializable saver function. It just creates a saver for any KotlinX Serialization type. The save part takes the original object and calls encode to SavedState. The restore part takes the SavedState and calls the code from SavedState. We get the full round trip with encode when saving, the code when restoring. So notice here that the type is mutable state list of any. That does means the backstack can hold any key type that you define. And that has some implications with KotlinX serialization. Since our backstack uses any, we need to use open polymorphism with KotlinX serialization. We would need to mark the base class, and in case of a polymorphism, all the subclasses with serializable, and register them. Behind the scenes, KotlinX serialization would add a hidden field called type, I think by default, and that's how the decoder knows which subclass to restore. But there is a small catch here, that is, you need to resist all no subclasses of polymorphism, otherwise you have an interface with a concrete type, and you don't actually know how to load this concrete type. So back to our example. We would need to define a custom serializers module to support polymorphism, which is inside the SavedState configuration. Inside the SavedState configuration, we set up the serializers module. Both are factory functions that allow you to pass configurations. And this configuration instance is going to be passed to remember serializable. This is how KotlinX serialization is going to do the mapping. So we're going to define a polymorphic any class that can be a product, a home, so on, and we resist all the subclasses. In a real app, you might have dozens or hundreds of subclasses to register. And again, if you forget and ask for that class, you might run in a runtime exception. Since we are using an N in this case, KotlinX serialization has no metadata to work with it. So N is basically the root of everything in the type system. So the compiler can't generate a serializer specific for it automatically. That's why we need to explicitly say polymorphic serializer just for this case, passing any in the configuration. So now let's look at the navkey interface. It's a marker interface for navigation keys. Any object or class that extends navkey must also be marked with serializable, so it can be saved and restored by the remember nav backstack function that we're going to see in a second. Why do we need this? Is basically because serializable is just an annotation. It doesn't give us a common type to tie everything together, so we don't have any common interface. By using this mark interface, we have one shared type that all keys must implement if you're using the nav backstack. That makes it possible to build a serializer that work across all navigation keys and provide helpers. So back to our example, we can now refactor this. This time, product implements navkey, and we now use polymorphic navkey to create our hierarchy. With an interface like navkey, we don't need to use anymore the polymorphic serializer, so we can drop that. We just need the configuration. It's a known type, so it's registered in the serializers module, and KotlinX can resolve through a normal serializer call. So the difference here is basically N is too generic, and you need to explicitly call polymorphic serializer, but with navkey or any interface class you control, KotlinX can discover the serializer via the module. Inside, we register all the subclasses, like product, home, and many more, like we did before. So now let's look at the remember nav backstack. That's a convenience function that builds a nav stack for you. It takes care of wiring up the SavedState serialization, the write configuration. So instead of you writing the code yourself, you can just call this function, and you get some defaults for you, and you just need to care about navigation logic. So this is the basic remember nav backstack. It gives you a nav backstack that's automatically remember in the compose hierarchy, across process depth. It's recoverable. Under the hood, it's going to use a nav backstack serializer, which is a public serializer that you can also use, together with remember serializable, which is also a public function. It's designed for open polymorphism by default with navkey type. All these destinations keys must be serializable and must implement the navkey, and you need to provide the SavedState configuration with serializers module that registers all navkey subtypes. On Android, there is also more convenient overload, but we're going to see that in a second. If we go back to our example, we can now replace it by remember nav backstack, but that doesn't change much, just remove 2 lines of code, so yeah. So now let's take a look at the navkey serializer. This one is Android only, it doesn't work in all platforms. It's quite opinionated, and it uses reflection to read this setup. So reflection, yeah. The goal here is to make the simple case easier, so you don't have to resist every subclass by hand. It can figure things out for you automatically, but of course, for complex setups, when you need full control, you can and should be using the serialization module. That is more of a making the easier case easier. There are some foot guns on this, so you're going to see in a second. So the NavKey serializer is a custom key serializer for NavKey. In serialize, we grab the class name of the value, and we encode the string element was the first element. And in this serialize, first we're going to read the class name, then we're going to call class for name, passing the class name to get that serializer, and this class.forName is a reflective call to load the class. So this is the Android-only overload for Remember Nav Backstack. If you notice, it doesn't accept a SavedState configuration. If you're passing a configuration, you have to pass the serialization module. That's by design. And this function is, again, only Android main. It's not available in common code. So if you're building a multi-platform app, you would need to use the serialization module. Instead, we call here Remember Serializable with a Nav Backstack serializer. But this time, we use the NavKey serializer, not the polymorphic one. And again, the NavKey serializer uses reflection in the hood. So while it makes the simpler case simpler, there is trade-offs. Like we can only make that work on JVM and Android. It's less performatic and a bit less safe. And for example, if you have type parameters in your key, we wouldn't be able to load these type parameters. So you need to have types without like classes without type parameters and generics. So this is the Nav Backstack class. It's a wrap around the snapshot state list. You can create one yourself if you would like to have your own backstack. T in this case must be a nav key, and we delegate for the mutable list implementation. We also delegate for the state object so Compose can observe change, and we also implement random access for some efficient functions. Yeah. So Nav Backstack here behaves just like a normal list, but it's also observable state in Compose. And this is the Nav Backstack serializer, the default one. It's also public. You pass in an element serializer for T, use that to build the snapshot state list serializer, which is provided by the SavedState Compose artifact. And that serialize is our delegate. It's basically a snapshot state list, the Nav Backstack. For serialize, we just delegate the function and use the delegate for the serialize. We decode the list again with the delegate and wrap it in a Nav Backstack. So now, if you go back to our code, we can take advantage of that by the Remember Nav Backstack that use the NavKey serializer. And on Android, we can remove the serializer module. And what we get when all of this comes together is this. You can just declare your keys, call Remember Nav Backstack, and things work. So one question you might be asking, why not just use field classes instead? That works fine if you have a single module app or in specific cases. But one thing of the sealed class is that all your subclasses must live in the same module. So in a multi-module project, that might get tricky. It might force you to put all the navigation classes into one module, and that not going to scale that well. But you can do that if you want, since it's a list. KotlinX Serialization is designed to be explicit. You resist every subclass. You have the compiler plugin to give you compile safety. That's the correct and predictable behavior, and it also avoids runtime reflection. But on situations like that, where you have keys that might be disjoint and be everywhere, yeah, it can get verbose. And also lead to runtime exceptions if you forget to resist specific subclasses. That's why we built the reflective serializer for Android. It's a trade-off for easier setup for the simpler case. But it doesn't replace the serialized module. And yeah, in Kotlin multi-platform, again, you would need to use the serialized module. And the KotlinX team has also actively been working improvements, like letting you resist just the sealed interface once instead of every single subclasses and deduce it from that, which is going to be a really nice improvement and probably the way to go once it's done. What that means in practice would be that if you have a multi-module app, and let's say you have an app module with several feature modules like feature 1, 2, whatever, Each feature would define your own sealed class nav keys inside that module. That module would have all the subclasses. And today in KotlinX Serialization, what you have to do is resist the parent, the sealed class topmost, and all of the subclasses, which is, again, a bit verbose. And you would basically need to go on each feature module, listing every key and wiring them all up in the app. With the improvement, once it's resolved this GitHub issue, you basically can just release the sealed class parent once, and then all of the subclasses will be discovered automatically. So everything here that you saw is built on top of public APIs. And you can reuse them if you want to use your custom implementations. You don't actually need to use any of that. That's one of the nice things about Navitree. So let's see what this looks in practice. Let's say you want to use your own types and your own serializers. Back to our example, you could still plug in custom serializers. If you stay with remember nav backstack, you can pass a SavedState configuration with your serializer module for custom serializers, polymorphism, contextual serializer, and so on. Or you can take full control, calling directly the remember serializable, and build a nav backstack with your own custom type that only accept that type. Here is one option for setting navigation keys. You can define an interface, my key, mark it with serializable with a custom serializer. You can maybe extend them with my key serializer, the nav key serializer that we provide, which is an open class. You can just, sorry. Yeah, for the backstack, you can call remember serializable, create a nav backstack, my key for the type, and now this backstack only accepts my key. You still avoid writing all the full SavedState configuration on Android, but yeah, you can now type it to a specific type. Here is another option. You can use sealed class again. You define your keys and arguments inside the serializable. Let's say you have other subclasses here. Then you create the backstack using remember serializable with the type nav backstack, key, etc. And because this is a sealed class, the compiler knows all possible subclasses. You don't need to pass a configuration as long as everything is in a single module, and it works. Or another example, another way. You could integrate with a view model. You could call in your my view model SavedState handle, use the saved function, return a nav backstack. This is going to be using KotlinX Serialization to restore, and ties to the view model SavedState. By the way, that's how the SavedState function looks like. It's very simple. It's just a delegate that when save, it takes the object and calls encode to SavedState. When restore, it takes the SavedState and calls the code from SavedState. It also takes care of some other stuff, but it's basically this. Another option, if you want more options, you can wrap that in a backstack into a navigator class. You can mark it singleton. You can provide it by Dagger. Now your navigator just holds a nav backstack of nav keys, and you can inject these in different parts of your app. So the point here is convenience is nice. We give you some stuff out of the box, but you are in the control, and you can basically send the nav backstack to the backend. You can write in the database. You can put in a view model. You can retain across configuration change. You can save it as a JSON. I don't know why, but and basically in Navitree, it's completely up to you. So to conclude, this works allows the navigation state to be shareable across all Kotlin multi-platform targets with some goodies for Android. That means Android, iOS, and desktop can use the same approach with serializers module and can share the navigation logic with navigation tree runtime artifact. If you haven't tried navigation tree yet, please give it a go and share your feedback. That's my talk. Thanks for listening.